All right, let's return to our discussion last time, and as we mentioned last time, what we're going to look at today is the concept of the basic power supply, simple power supply. And so last time I did a block diagram of a power supply, and let me redraw that. So as we mentioned last time, a power supply is going to have several different parts. First of all, you're going to have your 120 volt AC RMS voltage coming in at 60 hertz here in North America. And we're going to first convert that to a lower voltage. And so what comes out of here is some voltage Vs, which is going to be nothing more than an AC voltage with a lower amplitude. So this device here is called a transformer. And we're not going to cover the transformer in this class, but I'll briefly tell you that this is nothing more than a device where you're magnetically coupling two inductors. And so the voltage in this inductor induces a magnetic field, which couples into an inductor of a different size, and it will then induce another AC voltage, but of a different amplitude. So this is used very much in modern power transmission and distribution. Not really used so much now in modern power supplies. There are clever tricks people use in order to convert voltage nowadays that don't require transformers, because these things tend to be big and bulky. But we're going to just look at this old idea, this basic concept. And this idea, what I'm showing you here, is literally decades old in terms of how to design power supplies. So from here, for my transformer, I'm going to have some voltage Vs. And let's assume that voltage looks something like this. Let's say Vs is equal to 12 times cosine 120 pi t volts. So 60 hertz, omega is equal to 2 pi f. And I'm just representing this as a sinusoid. So here is my Vs voltage. And then I'm going to feed this into the rest of my circuit. So all of this goes into the rest of this, which is what this represents. So I've scaled it down. And the question is what does this look like? Well, if I were to take this, right now I've got a sinusoid with a magnitude of 12 volts, and so it goes between plus and minus 12 volts. That's what Vs looks like. So the first step is I want to rectify that voltage. Now we already know about rectifiers. We looked at simple diode rectifiers. We looked at a half-wave rectifier, and if I were to take a half-wave rectifier and connect it to that voltage Vs, we know what it would look like. We'd see something like this across this load. I'm going to call this voltage V1. We would see something that looked like this. So in this case, we would see the positive half of the waveform. We've already seen this in the lab, in homeworks. Now, the input voltage has a magnitude of 12 volts. Would this maximum voltage also be 12 volts? coming up the output is? No, not unless the diode is ideal. In a real diode, if that diode is turned on, we'd expect about 0.7 volts across that diode, correct? So really, what we're going to see here is a maximum voltage of about 11.3 volts due to the forward drop of that diode. All right? So this is a basic half-wave rectifier. That's the first step of converting AC to DC. But you know, there's something fundamentally wasteful about the half-wave rectifier. And that's the fact that you are throwing away the negative half of the input waveform. We just block it. We don't use it. But that's, in effect, available energy that we're not using. Wouldn't it be nice if somehow we could also take advantage of the negative going portion of that waveform? Well, yeah, it would be nice. And in fact, long ago, people figured out ways to do it. So this, we've been calling it a half-wave rectifier. Now let's talk about the full-wave rectifier. This is a more efficient way of doing diode rectification because it allows us to take advantage of both the positive and the negative waveforms at the input voltage. How do we make it work? Well, we do it like so. Instead of using one diode, I'm going to use 4 diodes. Now remember before when we looked at diodes and we showed how diodes could be used to steer the direction of current when we looked at that traffic light example? Well, that's what's going on here. These extra 3 diodes allow you to do a current steering trick. If we can always ensure that the current is flowing this direction through the load resistor, then we're always going to have a positive voltage appearing across V1. It'll always be positive. So let's look and see how we do that by doing these extra 3 diodes. Right. So let's look at this, and let's think about Vs being this AC waveform, and let's consider how this is going to work. And I'm going to redraw this over here. Let's look at one example. Let's assume that Vs is positive. So I'm going to redraw our circuit, and I'm just going to add a source to show that Vs is there. All right? If Vs is positive, positive current is going to flow that direction out of Vs. And then current's going to flow into the negative terminal like so. So we all remember that from 2112. So looking at this, let's look at our 2 diodes. So if the current flows into the top, it can go in 2 paths, D1 and D4. Which path can that current take? Can it go through D4? Can't do that because it'd be entering the cathode and coming out the anode. The only possible path is for D1 to go through, or pardon me, for the current to go through D1. And so in this case, I'm going to see this. So D1 is going to be on. Current's going to flow through D1. And then that current is going to flow into the top of the resistor, flow out the bottom of the resistor, and then it's going to travel back around until it reaches the junction of D2 and D4. All right? So looking at this, I see two possible paths, D2 and D4. Now you might look at that and say, can it flow through D4? It's at the anode, but is D4 going to be on? Well, no, because think about it. The most positive node in the circuit is the cathode of D4. The anode will be less positive because there's a voltage drop that it just traveled through for that V1, for the resistor, for that V1. So D4 is reverse biased. Even though it looks like the current can go into the anode, that diode is off. And so in this case, the only place it can travel is through D2. So in this case, D2 is on. It can't travel through D4. D4 is off. Nor can it travel through D3. D3 would have to flow through the cathode. D3 is also off. So in this case, when Vs is positive, the path the current takes has to be through D1, around this resistor, then through D2, and then back into the source, into Vs. Everybody see this? So we're just doing a current steering trick. Now let's look at the other case. What if Vs is less than 0? Once again, I'm going to go ahead and kind of draw this. So I'm going to take Vs, and since it's negative, I'm going to flip the polarity. And so in this case, current is going to flow into the negative end and out the positive end. So the direction of current, the flow of current is reversed. And in this case, we can look at this and very quickly prove to ourselves that if the current's going in this direction, the only possible path that the current can now take is through D3 and D4. So in this case, I now have this. So in this case, the current now travels through D4, once again enters the top of this resistance, flows back down, comes back around, and the only path for it now is for D3. So in this case now, D3 and D4 are on. And D1 and D2 are off. using the same logic we did just here a moment ago. We're just flipping the direction. So 2 diodes are on at any given time, and the current's flowing through those 2 diodes, but the current is being steered in such a way that it always enters the top of that resistor. And so the negative part of the waveform now becomes positive. In effect, these diodes are flipping how the input voltage is applied to the circuit. Very clever. Takes us 3 extra diodes. So in this case, I've got an output voltage V1. And over here, let's think about this. What is V1 going to be equal to? If both of these diodes are on, clearly I've got 0.7 volts across both those diodes. And so in this case, V1 must be equal to Vs minus the drops of those 2 diodes. So in this case, V1 is equal to Vs minus 2 times Vd, the drops across the diodes. So with the half-wave rectifier, I lost 1 voltage drop, 1 diode drop. With the full-wave rectifier, the price I'm paying is I've now got 2 diode drops in order to make the full-wave rectifier work. And over here, what I'll have is that V1 will be, when it's negative, V1 will be equal to minus Vs plus 2 times Vd, because once again, I'll have 2 diode drops. So I can take advantage of the positive and negative waveforms, but the penalty I'm paying besides the 3 extra diodes in this circuit is the fact I also have an extra diode drop. Regardless, this is an incredibly useful circuit. You do have the extra diode drop, but now you're taking full advantage of both the positive and the negative waveforms. Now, there are actually several different ways to do what we call full wave rectification. But this is one of the more popular ones, and this, in fact, this particular diode arrangement is called a bridge rectifier. There are other ways to do full-wave rectification, but the bridge rectifier is one of the simplest. And in terms of component costs, all you need is 3 extra diodes. So this is really a very popular technique, and you will see it used, all over the place even today. But if you look in the book goes over some other ways of doing full-wave rectification. I'm not going to spend time on them, but you can look at those yourself. Okay? So this is the first step in my power supply design. I've gone through rectification, and now I've got an output voltage coming out of the rectifier. What I have now is something that looks like this. Where now I'm capturing both halves of the waveform, but notice it doesn't quite touch. There's a little dead zone in between those peaks because obviously in order for this circuit to work, Vs has to be greater in magnitude than 2 diode drops in order to turn them both on. So there's going to be a little bit of a dead zone here where the voltage itself is going to be a little bit higher, the input voltage. And you're not going to see the full magnitude of the input voltage because of that 1.4 volt drop. And so you'll have a little bit of a dead zone whenever Vs is within the range of plus or minus 1.2 volts, or pardon me, 1.4 volts. Yeah? Well, I'm just saying the voltage is going to be negative, okay? And so V1 is now going to be a positive voltage, but it's going to be the negative of the negative value Vs. All right, so in other words, it's flipping in that, here's the Vs. It's flipping that negative value, which was, and then turning that into a positive value, and then once again subtracting, actually I should take that back. This should be, I think you just made a good point here. This should actually be minus 2Vd. You're correct, my mistake. I just realized I wrote that down wrong. That should be minus Vs minus 2Vd. Okay, you're correct, you're correct. So it's going to be a negative voltage, positive, but still minus the 2Vd. Correct. Thank you very much for pointing that out. All right. So here's our circuit. Now, I've now got a voltage, V1, which, as you guys can see here, is all of the same polarity. The only problem is it's not a constant voltage. I want a voltage that's constant. I want to turn this into a DC voltage, a voltage that's invariant with respect to time. So the next step is the filter. Let's take this and let us add a filter capacitor in order to stabilize our output. And I'm going to do that like so. So here's our bridge rectifier. Here's our load resistor. And I'm going to add a ground here just to be a little more 2112-ish. Let's put a proper ground on this. And I've got a constantly changing voltage, even though it is of only one polarity. And I'm now going to do this. I'm going to add a filter capacitor. Now we know from circuits 1 that capacitors store energy. And we also know that once a capacitor is charged up, it can discharge energy. And we also remember that it's an exponential charging and discharging path, is how RC circuits work. And in fact, that's exactly how we're going to treat this. We're going to think of this as a first order RC circuit. All right? Let's consider what is going to happen in this circuit. I'm going to kind of redraw this voltage from the bridge rectifier. Draw that out. Okay, so this is what we see. This is the voltage without a filter capacitor. Now we add the filter capacitor. What's going to happen? Well, I'm going to just illustrate that with a different color pen here. Okay. So let's assume we start with everything discharged. The capacitor is discharged. And we now apply Vs to our rectifier. So what's going to happen is Vs is going to rise. And as it rises, as Vs rises, what you're going to see is the capacitor is going to charge up. Because once these two diodes turn on, basically I'm going to have this voltage source connected across that capacitor. So that capacitor is going to charge right along with Vs. And so, well, actually Vs minus the two diode drops. So what we're going to see is this. The capacitor voltage is going to track the rectifier voltage, and that capacitor is going to charge up. So the capacitor charges up to the peak rectifier output. And then the rectifier, the input voltage to the rectifier starts to drop. And so the rectifier voltage would normally begin to drop, except in this case, with the capacitor, that doesn't happen. Once this voltage here begins to drop, the voltage across the capacitor, the energy in the capacitor, now sustains the voltage at this node. And so in this case, what we get is so as the magnitude of Vs drops to 0, C is going to maintain the output voltage at that output node. But it's not going to be a perfectly stable voltage. And the reason is the voltage is being maintained by the capacitor charges up. Now once the voltage across Vs starts to decline in magnitude, what you're going to find is all of the diodes will shut off because all the diodes will be reverse biased. The voltage at Vs is going to be less than the voltage at the output, and so the diodes can't turn on. But at the same time, the voltage across the capacitor doesn't remain stable because it's got a discharge path. It can now discharge through that resistor. So what you're going to see is this. So C maintains the output voltage at the output node, but now what we find is, but the voltage at the output is going to discharge through R. So the capacitor is going to discharge through that resistor R, and we're going to see the voltage start to discharge like so. In the meantime, Vs goes through its entire cycle. And then the magnitude of Vs starts to rise again. So somewhere along the line, the input voltage Vs is going to intersect this drooping voltage to the point where it's going to once again turn the diodes back on. And then once again, the capacitor is going to charge. So in this case, in this region here, all diodes are off. In this region, as Vs increases, 2 of the diodes are going to turn back on, and then the capacitor charges up again to the peak voltage. So 2 diodes turn on, and which 2 diodes it's going to be is going to depend upon whether Vs is going through its positive or its negative part of the cycle. And then, once again, the capacitor is going to charge up. Now, as the capacitor discharges, what kind of decay is going to occur here? As this capacitor discharges through R, what are we going to have? First order exponential decay, right? So in this region, this is first order exponential decay. In fact, if I did not have this next charge pulse coming along, how long would it take for the capacitor, for that voltage across that capacitor to discharge? 5 times RC, right? 5 time constants. So we've got that same exponential decay. And actually, I'm not really drawing this quite properly. It's more like so. So it's an exponential decay. It's only just a portion of it here before it gets intersected and turned back on again. But this is going to be exponential decay, as we've seen before. And that decay is going to be according to our first order math, our first order time constants. We've seen this before. Okay? So what we see now is this. We're going to see this type of voltage appearing at the output. And let me redraw this over here. Actually, let me redraw it up here. Now we're going to see an output voltage that looks like this. The filtered output voltage is going to look like this. So we're going to have some average DC value . But we're going to see this little discharge and charge wave is what we're actually going to see. We have a name for this. This behaves very much like an AC signal on top of a DC signal. And we call this voltage droop, or voltage ripple. So you'll see either one of those. Okay, so we think about this. This is due to the RC discharge. And here's a question. Can we alter the magnitude of that droop? Can we reduce the amplitude of that ripple? Well, how could we do that? Well, what is causing this droop? What's causing the fact is the capacitor voltage is discharging through that resistor R. I'm sorry? Higher frequency would do it, except that in our case, we're stuck with 60 hertz. But actually, you hit upon something very interesting, because we actually do this kind of thing in what are called switching power supplies. We actually do make the AC signal a much higher frequency, which in fact reduces that droop. But you're correct, you could do that. So that's one way. So that's one solution. Higher AC frequency. But in this case, like I said, we're assuming we're running off of our 60 hertz power mains. What's another way I could reduce the droop?
Adjust the capacitor?
Yeah, exactly. Let's make the capacitor larger. So to reduce the ripple, we can make the capacitor larger. And along the same lines, what's something else we could do? Make the resistor larger, right? Because doing either one, making R or C larger, means we have a larger time constant, longer time constant. Yes?
I guess physically what's happening when you make the capacitor bigger? Does that mean it?
Yeah, the capacitor is now storing more energy. So the capacitor stores more energy, therefore it's, in this case, since it's got more energy, the voltage is going to decrease more slowly as current flows through that resistor. So just tau is equal to RC. So remember, from 2112, we talked about this. The idea that if you charge up a capacitor to a particular voltage, it's going to decay away according to tau is equal to 5 RC. Okay, first order response. So same thing here. If I make either R or C larger or both, then the slope of the decay gets shallower and shallower. Yeah?
So it's like it is a low-pass filter.
It is a low-pass filter. That's exactly what it is. From the viewpoint of circuits 2, it's a low-pass filter. From the viewpoint of circuits 1, it's a first-order exponential decay. But it's actually, you're talking about exactly the same thing. So yeah, if you wanted to look at this from a circuits 2 point of view, I've got a capacitor, and the capacitor is creating a low impedance to the AC portion. And so that gets shorted out, and all that's left is DC, the low-frequency stuff. It's another way of looking at it. But I know some people in this room haven't had circuits 2, so I'm trying not to use circuits 2 terminology. Okay? So clearly, this will reduce the output ripple. And once again, it all revolves around the idea of the stuff we saw back in circuits 1. And in fact, that's exactly what you're going to see. Is typically, these capacitors tend to be large, tens or thousands of microfarads. And then when you look at a power supply and open it up, you'll typically see big capacitors in there, all right, because they have to store a lot of energy. We want to minimize this ripple, this AC droop, as much as possible. We want a clean DC supply. Now, incidentally, we notice there is another big advantage to doing this with a full-wave rectifier. Could I filter a half-wave rectifier? I mean, some people will say, well, Dr. Holman, since the capacitor is already doing the filtering, why not just use a half-wave rectifier? Well, I could do that. But what's the problem with a half-wave rectifier? Well, actually, you do it right here. The problem with a half-wave rectifier is this. The half-wave rectifier, let me see if I've got another pen here I can use. Here we go. The half-wave rectifier is only going to charge up every other waveform. So if I had a half-wave rectifier, it would do this. It would decay much, much longer before it hit its recharge cycle because it doesn't have that negative going waveform in order to recharge the capacitor. So the capacitor only gets recharged half as often. So if I have a half-wave rectifier, what is the drawback I'm going to have? More ripple, okay? Because it's going to take longer before I get this thing to recharge. Once again, it's effectively you're lowering the frequency, okay? That's what's happening here. Because now you're only getting every other waveform. So the full-wave rectifier works very well with the filter capacitor, and typically will make that filter capacitor big, as I said before. But you know, could we do better than this even? Could we somehow get rid of this ripple? Okay. Let's look at this. Remember we talked about voltage regulator circuits. And what did we say was one of the properties of voltage regulator circuits? Line regulation. They take variations in the input voltage and it reduces those variations because of the action of the diode. Well, you know, that tells us there's the next step. After the filter comes the regulator. So now I'm going to draw this circuit. Now let's do this. So what I'm going to do now is, I had the resistor and, the resistor and the capacitor, the RC. Now I'm going to separate them. And in between them, I'm going to connect a Zener diode and another resistor. So what have I done here? I've now added a shunt regulator, a Zener diode shunt regulator. So now I am even further regulating this. I'm going to call this R. I'm going to call it R sub L. That now becomes our new load. So now I've got an output voltage where the regulator's own line regulation reduces the effect of the ripple that much more. So let's kind of throw in some, let's come up with some numbers here. Let's say I've got a rectifier plus a filter capacitor. And let's say I went and I measured the ripple, and the ripple was 200 millivolts peak to peak. Now, that's just with the rectifier and the filter capacitor. Now I could reduce that by making the capacitor bigger, but instead, let's run it through a Zener shunt regulator. And let's say my regulator has a line regulation of 10 millivolts per volt. And of course, these are just numbers I'm pulling out of the air, okay, but reasonable numbers. So I've got 200 millivolts peak-to-peak ripple, but I've got a Zener regulator with a line regulation of 10 millivolts per volt. So if I connect the Zener regulator to the output of my filter capacitor, what would I expect the ripple at the output will be on the other side of that Zener regulator? Well, that's going to be 0.01 times 200, isn't it? So here what we're going to get is, if I add these two together, I'm going to get 2 millivolts peak to peak output ripple. And now that's getting pretty good. Now we've got an AC component that's down in the millivolts. And in fact, if we improve upon this circuit, we can actually lower it further than that. And so when we're doing power supply design, one of the things people will specify in power supply design is, what is the maximum amount of output ripple allowed? And then they will specify that, so you've got to design the power supply to stay within those limits. Okay? Well, there's still an issue here, and the issue is this. I still have the problem is changing that resistor value, that load value, is still going to change the value of VO due to output loading. Is there yet one more component that I can add to this circuit to improve it even further? What can I add to it? Op amp, absolutely. We talked about this before. Why can't I just take this and do this? I'm going to separate that RL resistor, and instead I'm going to do this. Now the input current to the op amp is essentially 0. And now I'm separating RL so that now I am eliminating loading effects. So now the op amp itself, a unity gain buffer, is going to supply the current to the op amp. So just as we saw before, that op amp is going to severely reduce any type of loading effects. Not perfectly. No op amp is perfect. But it's going to drop something perhaps in the millivolts down into the microvolts. Yeah?
How do you power the op amp?
Well, the op amp typically is going to be powered generally by the same voltage you have back here. Okay? So in other words, op amps actually have quite a bit of resistance to what they have power supply rejection. And so typically you can either power the op amp from a voltage further back here from some other supply. So this is kind of a simplistic way of doing it. But normally what you'll do with these is these will typically be unipolar op amps. We'll ground it on one end, we'll connect it to some VDD, and normally the VDD will use something we pull back further here on the filter capacitor chain. So we may, for example, pull it back such that, well, in this case, normally we're going to have to pull this back from some higher voltage to make sure that the VDD is working. So this may come, for example, from some other bias string somewhere else in the circuit. So I'm just not bothering to draw that.
How does that not reintroduce the ripple?
Because the op amp has what's called power supply rejection. It can have a lot of ripple on it, but the internal feedback of the op amp minimizes that effect. Again, that's beyond the scope of this course. If you take more advanced courses, you'll find that power supply, or op amps have what's called power supply rejection. And there's something called the power supply rejection ratio, which means that op amps can actually tolerate a certain amount of ripple on their own power supply rails, and it will not appear at the output of the op amp, which is a very useful property. Yeah?
Did you mean not to include the resistor right before the capacitor?
Well, here, we don't need it here, okay? So you're saying this resistor right here, R sub L?
No, the resistor like between the bridge rectifier and the capacitor.
You mean here?
Yes.
Well, there was no resistor here. The resistor was always in parallel with the capacitor. Okay, it was always in parallel. The series resistor is here on the other side. Okay. But yes, obviously you need to get that voltage from somewhere else in the circuit. All right, but once again, that's beyond the scope of what I'm trying to show you guys here. Yeah?
Can you explain one more time how the Zener diode regulates
The Zener diode regulator, yes. Well, this is, once again, this is a shunt regulator. We talked about this before. So I've got a rippled voltage coming in. So what does a shunt regulator do? It takes a varying input voltage and keeps that output voltage stable. We did those calculations before, right? So in this case, if we think about it like so, remember how we calculated line regulation. So a large input swing causes a very, very tiny change at the output. So we've already covered this exact concept. This is no different. This is no different. This is line regulation and a voltage regulator. And you can actually prove this works in either the large signal or the small signal domain. do that calculation. So look back in your notes when we did line and load regulation for a Zener diode. Nothing's different here, except now the input voltage variation we're seeing is not some huge swing, it's the actual ripple. And so we're now rejecting that ripple. But the same line regulation principle still holds. Okay? So this, in a nutshell, is a very simple power supply. These are the kinds of power supplies people were building 50 years ago. Nowadays, power supply design is a lot more sophisticated than this, what we're doing here. But the basic principles still hold. Although, if you ever do get a chance to take a class in modern power conversion from somebody, for example, like Professor Witulski here at Vanderbilt, take it. Believe me, it's a great course, because if you want to learn how modern electronics are powered and how we do modern AC and DC to DC voltage conversion, it's going to be a lot more sophisticated than this. But here we kind of see the basics. And in fact, the big linear lab supplies you have on the benches in the electronics lab actually work pretty much on this principle. A little more sophisticated, obviously, because you can actually vary the voltage. But the general idea is what you see here. All right. Questions? Yes?
Does the reverse breakdown voltage of the Zener diode have to be close to the DC output?
Well, obviously, yes. The reverse breakdown voltage is going to set the DC output voltage.
Oh.
Yeah, it's got to, right? All right. So in other words, what you're going to normally see is this. Okay, you're going to have something that looks like this. And then you're going to have a voltage at the output that's going to be a lower value, which is set by VZ. So we're going to have VZ, we're going to have an input voltage with a ripple, then we'll have a VZ, which is a lower voltage, which is the breakdown voltage of the diode.
What I meant is you can't have VZ too low.
Then it turns off, exactly.
No, I meant too low compared to the, like too much of a voltage. Like the Zener diode can't take so much current.
Well, the Zener diode can take as much current as you design it for. In other words, you can actually spec the Zener diode. You want to make sure you don't exceed the power dissipation of the Zener, right? But so obviously, you want to make sure that whatever shunt current is flowing through that Zener diode doesn't exceed the specifications, okay? But yeah.
What is that drop typically?
What?
Between VZ and the ripple?
You mean from here to here?
Yeah.
It's going to depend upon the power supply you design. Okay. Obviously, it's going to be some amount of voltage, okay, because the input voltage has to be greater than or equal. Because keep in mind that the input source voltage has to supply the Zener diode, and there's going to be a drop across that RS. Okay. So, but that's going to depend upon how you design the circuit. Yeah.
So I was just making sure. So when you have the rectifier for the capacitor, the 200 millivolts peak, that's the blue line right there.
Yeah, that was this. That was this blue line.
And then the
Okay.
2 millivolt peak would be your final.
That'll be the output ripple at the output of the circuit itself, at the output of the Zener regulator. So what you're going to see is this. You'll have your input voltage with a large ripple. You'll have an output voltage which is going to be lower, which is going to be set by the Zener diode. And then we're going to have a small amount of ripple on top of that, which is going to be the line, that's going to be the line regulation of the Zener diode. Okay? Questions? Yeah. Up here? Before, I'm sorry. Before I inserted it. No, before I inserted the op amp. Oh, I see what you're saying. Yeah, before I inserted the op amp, I had that. So I connected the load resistor directly to the output of the Zener regulator.
So how does the op-amp limit the voltage drop?
Well, in this case, I have a loading effect. If I change the value of RL, the value of VO changes. Load regulation. Remember, we talked about that last week, too. There's line regulation, there's load regulation. The voltage across the diode, VO, is going to change due to both. Adding the op amp reduces the load, or improves the load regulation, I should say. It reduces the loading effect due to RL on this circuit, because once we put in that op amp, then the current going in is 0. So the value of RL does not affect the input current flowing into the op amp. So that improves load regulation. So we saw exactly this kind of thing last week, how you actually eliminate the loading effect on the output of a voltage regulator is by inserting that op amp. Okay? So the op amp improves load regulation. The Zener diode improves the line regulation. But between the two of them, you have much better performance than what you had before. All right? Other questions? Yeah?
Could you remind me what an op amp does?
I'm sorry?
Just quickly remind me what an op amp does. Like, what does it do?
What does the op amp do? Okay. Well, then, no, unity gain is what this is. So here's our VO. Okay, remember, think about the properties of an op amp. What's the input current to an op amp? 0. All right? So there's no current flowing into this node, regardless of the value of RL. And then because it's unity gain, I've got VO here. I've got a virtual short circuit at the input of the op amp because of negative feedback, which means that voltage is VO, which means this voltage is VO. So I've got the same voltage here as I do here, except now this voltage is independent of the value of the load resistor, because this current is 0, and remember, the output of an op amp behaves like a dependent voltage source. And so all the current flows out of the op amp, and that supplies our load resistor. All right? So basic lesson. And incidentally, I think you're going to be building one of these in one of your labs coming up. You're going to actually build an op amp circuit to do a super diode circuit. So you're going to be forced to relearn this. Or if you haven't taken circuits 2, you haven't seen op amps. But believe me, you'll still be able to do the simple circuit we're going to do in the lab. Any more questions? All right. Okay. Let us now, very quickly, I want to wrap up with a discussion of something that's not really covered very well in the book. And for reasons I do not understand, the authors of the book in the newest edition cut out some material that I still think is extremely valuable, so I want to spend a little bit of time talking about it. And that's diode limiters and diode clippers. So here's another application of a PN diode. What are diode limiters and diode clippers? And they tend to be very related in terms of what they do. So you'll see these names used interchangeably quite often. But the idea is you'd use a diode in order to limit the maximum or minimum value of a voltage. And let's start with what we call just a simple limiter. And when you think about it, what I'm going to draw here makes kind of sense, based on what you guys have seen so far. Let's say I've got a voltage Vn, an input voltage, connected to a resistor, and then I've got a voltage Vout that I'm taking across that diode. Now, let me look at Vn, and I'm just going to take Vn and I'm going to sweep Vn over a range of input voltages. Let's plot Vout versus Vn. Now, when Vn is negative, what do I know about the state of that diode? It's got to be off. It's going to be reverse biased. So if it's off and it's reverse biased, then this becomes an open circuit. If it's an open circuit, there's no current flowing through that resistor, and V out is simply equal to Vin. So for negative voltages, I see this. V out is simply equal to Vin. So I have just a slope of 1. Then I start making Vn positive. And Vn climbs up until we hit what point? The forward bias on voltage of the diode. So at some point, I'm going to hit that input voltage, and then the diode turns on. And what I'm going to find now is once that diode turns on, no matter what current flows through that resistor, the voltage drop across the diode is essentially constant. And it's going to be about 0.7 volts. So I can have a range of positive and negative voltages, but the positive voltage is limited to a maximum value of 0.7 volts. It's a limiter. Now, this is a positive limiter. Could I also make a negative limiter using the same concept? Yeah, what would I need to do to make a negative limiter? Flip the diode around, right? So I could do this instead. So in this case, now I've got the same circuit, except now this diode turns on if Vn becomes too negative. And so in this case, I'm going to see this type of behavior. For positive voltage, the diode is off. V out's equal to Vn. For a negative voltage, when I get down to minus 0.7 volts, once again the diode turns on. And in this case, it limits the negative going excursion. Well, it turns out this property is very, very useful. We are limiting, sometimes you'll sometimes see these circuits called clippers or even clamps. It's the idea that the diode turns on and then prevents the voltage from going past a certain limit. Okay? So this is a simple limiter. This is a negative limiter. These are simple limiter circuits, but we can be more sophisticated than this. Let's draw some other limiters. Let's draw a limiter circuit that's based on some Zener diodes. So it's called a double limiter. Let's take our limiter circuit and let's do this. Now here I've got two Zener diodes back to back. And you look at that and you kind of wonder, how's this supposed to work? Well, if you think about this circuit, in order for current to flow through these two diodes, one of them has to be in reverse breakdown and one has to be forward biased. And you can forward bias a Zener diode. It works like any other PN diode if it's forward biased. So if I sketch V out versus V in, at low voltages, V out is just equal to V in. Both diodes are off. But if I increase the magnitude of Vn, either positive enough or negative enough, it reaches a high enough voltage, one of these diodes is going to go into breakdown while the other turns on. That way current can either flow this way or that way. So what we're going to see is this. We're going to see that this circuit, the diodes are going to turn on when I get to a voltage Vz plus Vd. So in this case, this diode turns on in forward bias. This diode turns on in breakdown. So V out becomes Vd plus Vz if it becomes positive enough. And then at that point, once again, it goes into limiting action. And of course, if we go negative, then minus Vz minus Vd. And I will get a symmetrical limiting on the negative side if I have a sufficiently negative voltage. So here's the same limiter idea I had a minute ago, except now it's on both sides of the waveform, positive and negative. And also, I can adjust where the clipping takes place by choosing the value of my Zener diode. Very handy trick. Another circuit. What about that circuit? What's that going to look like? Well, that looks like nothing more than the simple limiter I just did a moment ago, except now I've got two diodes, front to back. Okay? Flipped in both directions. And what's that going to look like? Well, in this case, for low voltages, near 0 volts, neither diode turns on. If the voltage becomes too positive, that one turns on. If it becomes too negative, that one turns on while the other stays off. And so in this case, when I look at V out versus V in, I'll see this. It will limit between plus and minus 0.7 volts. So it's the same idea as a simple limiter, except now it's getting both sides. So there are all kinds of clever little tricks you can do. Now, incidentally, this type of thing is used quite a bit in something you guys have all heard lots of, music. Okay? If I were to take a sine wave, for example, a musical note, and I were to take this and run it into a clipper circuit like this, what would I get? I get something that looks like this. It's something that gets chopped off, top and bottom, by that clipper. So what's going to happen to that music? It's going to distort. It's going to sound bad. If you ever turn up the volume too loud on stereo and it starts to sound gargly and distorted, you're causing a limiting effect. You're exceeding the ability of the speakers or the earphones to capture those full amplitudes, which is probably a good thing because it would blow out your eardrums. But, okay. There are times, though, when distortion sounds good. For example, anybody here play guitar? Okay, you ever played a guitar? You ever use something that just basically adds distortion to the way the guitar sounds? Some distortion sounds good in music. So there are times when we deliberately introduce it, and one of those things is in for electric guitar. So, you probably use something that would actually introduce that. So some distortion's good. Now, all these limiter circuits I'm looking at, these are all called hard limiters. But there's one other type of circuit that's called a soft limiter, which behaves a little bit differently than this. Let's take this same circuit we just did, and let's look at the soft limiter. here's a soft limiter, which is nothing more than that Zener diode circuit we did a minute ago, except I am now going to add a resistor to it. Now I'm going to take my output voltage across the two Zener diodes plus an extra resistor R1. When this limits, I'm going to have an additional voltage drop across that R1, which is going to increase as the current increases. And if I look at how this circuit works, it works like so. Now I'm going to have this kind of behavior. I'm going to hit a limit point, VD versus VZ, except now I'm not going to have a flat limit because now I have the voltage drop across that resistor. Instead, I'm going to see this. The slope is going to change. And you can prove to yourself that that slope is going to be equal to R1 over R1 plus R2. So it's not a flat limiting, it is a sloped limit. So with what we call a soft limiter, we'll see this. Soft limit is going to look like this. Here's your input, and your soft limit is going to behave like this. I'll hit my limit, and then it'll just reduce the amplitude in the limited region. So here's soft limiting. So here, it's not flat, but I am reducing the slope, and so the amplitude is going to be reduced in that soft limit region. Now, once again, we use this in audio equipment. And why? Because hard limiting sounds very harsh to the ears. You hear that distortion. Soft limiting, you're just preventing the sound from getting too loud, but you're not distorting it that badly. And so it is a cleaner way of limiting that people will use, for example, in high fidelity audio. So this also is used a lot in audio. Okay? Next time we will look at a few more diode circuits, and then we'll wrap things up. And then on Thursday, we will begin the next interesting part of this class. We're going to leave diodes behind and begin looking at the MOSFET transistor. See you guys on Thursday.